July 15th, 1945, Bovingdon Airfield, England. The massive German bomber stretched 72 feet from nose to tail, longer than a B-24 Liberator. Its wingspan, 103 feet. But Colonel Harold Watson saw something that made no sense. 4 propeller blades per engine, yet only 2 engines visible on the entire aircraft. Technical Sergeant Mike Romano emerged from beneath the starboard wing, his Brooklyn accent cutting through the morning air. "Colonel, this thing's supposed to haul 13,000 pounds of bombs to London, but I'm only counting 2 motors." Watson had 32 years of aircraft maintenance experience, from Jenny biplanes to B-29 Superfortresses. He'd never encountered anything like this. Inside those sleek nacelles, German engineers had hidden their most ambitious innovation: 2 complete Daimler-Benz engines, coupled together, geared as one. 2950 horsepower from what appeared to be a single mount. The Luftwaffe called it their masterpiece of engineering, the future of aviation. What American engineers discovered inside would change everything they thought they knew about German innovation. Watson circled the aircraft with the methodical precision of a predator, studying unfamiliar prey. The Heinkel. He 177 stretched before him like a testament to German engineering ambition, sleek, imposing, and somehow fundamentally wrong. Romano knelt beside the starboard nacelle, running his hands along riveted aluminum that still bore scorch marks from its final flight. The Brooklyn mechanic's fingers traced patterns of heat damage that told stories Watson wasn't sure he wanted to hear. 32 years I've been crawling around aircraft engines," Watson muttered, crouching beside his sergeant. "From wood and wire jennies to the most advanced bombers in the world. Never seen anything like this configuration." Romano's laugh held no humor. "Yeah? Well, I got 15 years of busted knuckles and grease under my fingernails, and this thing's got me stumped too. Look at these access panels, Colonel. You see how they're positioned?" Watson leaned closer, his flashlight beam revealing a maze of maintenance openings that seemed designed by someone who had never actually serviced an aircraft engine. The panels overlapped in impossible configurations. Some required removing others just to reach basic components. Others appeared to provide access to empty space while leaving critical systems completely unreachable. "Christ," Watson breathed. "How did they expect anyone to work on this thing?" The question hung in the morning air as both men began their systematic examination. Watson had trained his teams to approach captured German equipment with healthy skepticism, tempered by professional respect. The Luftwaffe had produced some genuinely innovative designs. The Messerschmitt. Me-262. Jet fighter, the Focke-Wulf 190 series. Aircraft that pushed engineering boundaries in ways that demanded careful study. But this bomber felt different. Not innovative, desperate. Romano disappeared into the engine bay through an access hatch barely large enough for a man his size. Watson heard the sergeant's muffled curses echoing from within the nacelle, punctuated by the metallic scraping of tools against aluminum and the distinctive sound of someone trying to reach components positioned just beyond human limitations. "Colonel, you better get in here." Romano's voice carried an edge Watson recognized from 2 decades of working with experienced mechanics. It was the tone reserved for discoveries that changed everything. Watson squeezed through the access hatch and found himself in a mechanical nightmare that defied every principle of aircraft maintenance he had ever learned. His flashlight revealed 2 complete Daimler-Benz DB605 engines, crammed into a space that should have housed one. They were coupled together through an elaborate gearbox system, their crankshafts synchronized to drive a single propeller shaft. The engineering was undeniably sophisticated and utterly impractical. "Look at this coolant setup," Romano said, directing Watson's attention to heat exchangers positioned where no human hand could reach them. And these exhaust manifolds, they're running right through the hottest part of the installation. No wonder this thing's been on fire. The scarring Romano referenced covered every internal surface Watson could see. Deep, heat-damaged metal that spoke of repeated thermal failures. Cracked welds where expansion and contraction had stressed joints beyond their design limits. Oil stains that mapped a pattern of chronic leaks no maintenance crew had been able to permanently fix. Watson ran his fingers along cylinder heads that showed clear signs of overheating damage. The metal felt rough where heat had changed its molecular structure. These engines have been cooking themselves from the inside, he said. The coupled configuration traps heat that would normally dissipate through separate nacelles. Romano's flashlight illuminated a service manual clipped to the engine bay wall, pages and pages of German technical instructions that read like a maintenance manual written by committee. Watson's limited German was sufficient to understand the basic procedures, and what he read made him shake his head in professional disgust. "Look at this procedure for changing spark plugs on the rear cylinders," Watson said. "First, remove the propeller. Second, disconnect the engine coupling. Third, remove the forward engine mount, just to reach components that should take 15 minutes to service." Romano emerged from deeper within the nacelle, his coveralls now thoroughly blackened with oil and soot that had accumulated despite the aircraft sitting idle for months. "Colonel, I found something else. You know how they coupled these engines together? The synchronization system, it's more complex than the engines themselves. And if one half fails, the whole thing has to be shut down. Turn a 4-engine bomber into a twin in the middle of a combat mission." Watson played his flashlight across the coupling mechanism Romano indicated. The engineering was elegant in theory. 2 engines driving a common output shaft through precisely machined gears that maintained perfect synchronization under all operating conditions. But the complexity required dozens of additional components, each representing another potential failure point, each positioned where access required major disassembly. This is what happens when engineering requirements get written by people who never have to maintain what they design, Watson said. Some staff officer decided German bombers needed a dive bomb, so the aerodynamics had to be perfect. Clean lines, minimal drag. The engines had to be coupled to fit the profile. Romano nodded toward documentation scattered throughout the engine bay, maintenance logs that told a story of chronic problems and impossible repair schedules. "According to these German records, Colonel, this bird spent more time in the hangar than in the air. Average time between engine fires, 100 flight hours. Time to replace a coupled engine, 47 hours. Compare that to 12 hours for a normal installation." Watson began documenting everything with the systematic thoroughness that had made him the Army Air Force's most trusted technical evaluator. Each photograph captured not just the mechanical configuration, but the evidence of its fundamental flaws. The heat damage, the access problems, the complexity that transformed routine maintenance into major surgery. The morning sun climbed higher as both men continued their examination, but Watson's initial excitement had transformed into something else entirely. This wasn't German engineering superiority. This was German engineering desperation, brilliant minds forced to solve impossible problems with solutions that created worse problems. By noon, Watson understood that the He-1 77's most advanced feature was actually its most crippling weakness. The coupled engines that looked so innovative from the outside had doomed the aircraft from the moment someone decided elegance mattered more than engineering sense. The conference room in Berlin's Reich Air Ministry reeked of cigarette smoke and the particular tension that accompanied impossible demands. Colonel Ernst Udet paced behind the polished table where Germany's most prominent aircraft designers sat in uncomfortable silence, their notebooks filled with specifications that defied the laws of physics and engineering common sense. October's gray light filtered through tall windows, casting shadows that seemed to emphasize the weight of decisions being made without adequate consideration of their consequences. Udette's fist struck the table with enough force to rattle the coffee cups and technical drawings scattered across its surface. "Sturzkampffähig," he shouted, his voice carrying the authority of a Great War ace who had somehow found himself responsible for industrial-scale aviation decisions that bore no resemblance to the individual combat he understood. "Every bomber we build must be capable of precision dive bombing. No exceptions." Ernst Heinkel adjusted his wire-rimmed glasses and studied the requirements document that had arrived from the technical office 3 days earlier. Maximum bomb load in a dive, 2,200 pounds. Service ceiling with full load, 21,000 feet. Range, 1,700 miles. Each specification, taken individually, represented achievable engineering goals. Combined into a single aircraft requirement, they created contradictions that no amount of German engineering precision could resolve. "Herr Colonel," Heinkel began carefully, his voice carrying the measured tone of an engineer who had spent decades translating political demands into mechanical reality, "dive bombing requires structural strength and aerodynamic cleanliness that conflicts with strategic bombing payload requirements. The Americans and British have chosen to specialize. Fighters for precision attack, heavy bombers for strategic missions." Udette's expression hardened with the particular frustration of a man whose flying experience had taught him to trust his instincts, but whose political position required him to demand innovations that contradicted those same instincts. "The Führer has made it clear that German aircraft must exceed Allied capabilities in every category. We cannot afford to specialize. We must dominate." The room fell silent as each designer contemplated the impossible mathematics of the requirement. Traditional four-engine bombers, the American B-17, the British Lancaster, achieved their strategic capability through brute force engineering. 4 separate engines in 4 separate nacelles, each accessible for individual maintenance, each capable of independent operation. But their bulky, high-drag configurations would never survive the 400-mile-per-hour terminal velocities required for effective dive bombing. Heinkel's mind raced through potential solutions, discarding conventional approaches as quickly as he conceived them. Wing-mounted engines created too much drag and structural stress for steep diving. Buried engines eliminated accessibility. Push-pull configurations complicated weight distribution beyond acceptable limits. But there was one possibility, radical, elegant, and theoretically feasible. "What if we couple the engines?" Heinkel said, his voice carrying the excitement of an engineer who believed he had found the key to an unsolvable problem. 2 DB605s geared together in a single nacelle, all the power of 4 engines with the aerodynamic profile of 2. The concept hung in the cigarette-hazed air like a promise of technological salvation. Udette leaned forward, his political instincts recognizing something that sounded revolutionary enough to satisfy the Reich leadership's demand for German technical superiority. The mathematics appeared compelling. 2 coupled engines producing 2950 horsepower while occupying 40% less frontal area than conventional 4-engine installations. Heinkel began sketching on the conference table's leather surface, his pencil outlining nacelles that looked sleek and purposeful compared to the bulky engine installations that characterized existing bombers. "The DB606 power system," he continued, warming to his theme as the engineering challenges transformed into design opportunities in his imagination. "Perfect synchronization through mechanical coupling, streamlined installation, dive speeds exceeding 400 miles per hour." Other designers around the table began nodding as Heinkel's enthusiasm infected the room. The coupled engine concept offered something more valuable than technical innovation. It offered the possibility of satisfying impossible political requirements through engineering cleverness. No one mentioned maintenance accessibility. No one discussed heat management in confined spaces. No one considered the implications of cramming two 12-cylinder engines into a space designed for one. Udet studied the sketches with the focused attention of a man who recognized that his career depended on delivering aircraft that could satisfy conflicting demands from superiors who understood neither aviation nor engineering limitations. The coupled engines looked sophisticated, modern, decisively German in their technical audacity. They represented exactly the kind of innovation that could demonstrate Luftwaffe superiority over the mundane practical approaches favored by Germany's enemies. "How quickly can you have a prototype flying?" Udet asked, his question carrying the urgency of political timelines that bore no relationship to engineering development schedules. Heinkel's confidence grew as he contemplated the project that would establish his reputation as Germany's most innovative aircraft designer. 18 months for first flight. 24 months for production aircraft. We can have operational squadrons equipped by 1941. The promise echoed through the ministry building like gospel, carrying the sweet fiction that complex engineering problems could be solved through determination and German technical excellence. Orders began flowing from the conference room before the meeting officially ended. 1,000 aircraft, priority production status, unlimited development resources. Nobody consulted the mechanics who would have to maintain the coupled engines. Nobody asked the pilots who would have to fly aircraft with twice the normal number of potential failure points crammed into half the normal space. Nobody questioned whether theoretical elegance could overcome fundamental physical limitations when aircraft operated under combat. Conditions that stressed every component beyond design margins. The decision was made with the particular blindness of institutional authority that confused sophisticated engineering with practical engineering. The He-177 would become Germany's most advanced bomber through the simple expedient of cramming more complexity into less space and calling the result innovation. The maintenance nightmares, the chronic fires, the operational limitations that would doom the program, all of that lay hidden in the future, invisible to men who measured engineering success by theoretical performance rather than practical reliability. In the months that followed, as Heinkel's design teams worked feverishly to transform the coupled engine concept into flying hardware, the fundamental flaws remained buried beneath layers of technical optimism and political necessity. The frozen airfield outside Stalino stretched endlessly under December's brutal sky, its concrete runway scarred with black patches that marked where a 177 engines had caught fire and burned. Hauptmann Klaus Fischer pulled his leather flight jacket tighter against the minus 15-degree air and watched his ground crews work with the methodical desperation of men who knew their lives depended on machines that seemed designed to kill their operators. Feldwebel Ernst Kruger emerged from beneath the starboard nacelle of Fischer's aircraft, his face blackened with soot and oil that had frozen into a mask of professional frustration. "Herr Hauptmann, the oil cooler lines have cracked again. Third time this month on this bird. The coupled engines run so hot that metal fatigue is destroying components faster than we can replace them." Fischer nodded grimly as he surveyed the maintenance chaos that had become routine for Kampfgeschwader 40. Across the flight line, 6 He-1. 77s sat with their engine cowlings removed, exposing the mechanical nightmares that Heinkel's designers had created in pursuit of aerodynamic perfection. Ground crews worked in shifts around the clock, but the coupled DB606 power systems failed faster than human hands could repair them. The mathematics of maintenance had become brutally simple.
Each He-177 required 47 hours of work to replace a coupled engine compared to 12 hours for conventional installations. But the real killer was accessibility. Servicing components buried deep within the coupled nacelles required removing half the wing structure. Critical repairs that took 15 minutes on a Junkers 88 consumed 3 days on the He-177. Fisher's logbook told the story with stark numerical precision. January had begun with 12 operational aircraft and 4 in maintenance. By February, only 8 remained flyable while 8 underwent repairs. March brought the crushing realization that his squadron possessed just 3 operational bombers, while 13 sat grounded with
mechanical problems that his maintenance crews could not solve fast enough to matter. Kruger led Fisher to the aircraft's starboard nacelle, where access panels revealed the source of their chronic problems. 2 DB605 engines crammed into a space designed for 1 generated heat loads that no cooling system could adequately dissipate. Exhaust manifolds, stressed beyond their design limits by thermal cycling, developed cracks that allowed superheated gases to escape directly onto fuel lines and electrical systems. The result was predictable and terrifying. "Look at these cylinder heads," Kruger said, directing Fisher's attention to metal that showed the distinctive discoloration of repeated overheating. "The rear cylinders run 50 degrees hotter than the forward ones because air can't circulate properly through the coupled installation. We're cooking these engines from the inside, and there's nothing we can do about it." Fisher studied maintenance records that documented failures occurring with mechanical regularity. Engine fire rate, 1 incident per 100 flight hours. Critical component failures requiring major disassembly, 1 per 50 hours. Complete power system replacement, 1 per 200 hours. The numbers painted a picture of aircraft that spent more time being repaired than flying combat missions. The operational implications were devastating. When one half of a coupled engine failed, both halves had to be shut down immediately. A 4-engine bomber suddenly became a twin-engine aircraft with flight characteristics that no pilot training had prepared crews to handle. Bomb loads had to be jettisoned. Missions had to be aborted. Aircraft had to attempt emergency landings with power systems that could fail without warning. Oberfeldwebel Hans Miller approached through the snow, his face carrying the particular exhaustion of a maintenance chief who had watched too many aircraft burn despite his crew's best efforts. "Herr Hauptmann, we've lost another bird. Lieutenant Zimmerman's aircraft caught fire on approach." The starboard coupled engine seized, and the fire spread faster than the crew could respond. "They got out, but the aircraft is a total loss." Fisher closed his eyes against the image of flames consuming another He-177, another piece of equipment that had cost Germany resources she could not afford to lose. The coupled engines that looked so elegant in Heinkel's promotional photographs became death traps when thermal stresses exceeded design parameters under combat conditions. The dive bombing requirement that had driven the entire program proved equally problematic in operational reality. German pilots reported that the He-177 became uncontrollable in dives steeper than 15 degrees. The coupled engine's massive gyroscopic effects, combined with the aircraft's forward center of gravity, made recovery from steep dives virtually impossible. The precision dive bombing capability that had justified the program's existence simply did not exist. Muller handed Fisher a maintenance report that summarized their squadron's operational status with devastating clarity. "Sir, we currently have 19 aircraft assigned to the unit. 3 are operational, 7 are undergoing engine replacement. 5 have fire damage requiring major structural repair. 4 are waiting for replacement parts that don't exist because the coupled engine components are too complex for field manufacture. Fischer studied the numbers that represented the collapse of German strategic bombing capability on the Eastern Front. The He-177, designed to devastate Soviet industrial targets, could barely maintain a single operational aircraft per squadron. Meanwhile, Soviet production continued unimpeded while German resources were consumed maintaining aircraft that could not reliably complete combat missions. The irony was not lost on experienced pilots like Fischer. The Luftwaffe possessed the most technologically advanced heavy bomber in the world, and it was useless. American B-24s, with their simple, accessible four-engine layouts, flew combat missions daily while maintaining operational readiness rates above 80%. British Lancasters struck German targets nightly with mechanical reliability that German engineers had sacrificed in pursuit of theoretical perfection. Kruger returned from inspecting another aircraft, his expression grim. Herr Hauptmann, Lieutenant Weber's bird just developed cracks in the coupling gearbox. The entire power system will have to be removed and rebuilt. That's another 2 weeks minimum, assuming we can find replacement parts. Fischer nodded, adding another aircraft to the maintenance list that had become longer than his operational roster. The coupled engines that promised to revolutionize strategic bombing had instead guaranteed Germany's defeat in the air war through mechanical complexity that exceeded human ability to maintain under combat conditions. The Eastern Front continued its brutal progression, while Germany's most advanced bombers sat grounded by engineering decisions made in Berlin conference rooms by men who had never changed spark plugs in sub-zero temperatures or watched aircraft burn, because accessibility requirements had been sacrificed for aerodynamic elegance. Watson's final report landed on Pentagon desks in September 1945 like a technical bombshell that would reshape Allied understanding of German aviation engineering. 47 pages of systematic analysis accompanied by 312 photographs and detailed engineering drawings documented the complete failure of what German propaganda had proclaimed as their most advanced strategic bomber. The conclusion struck at the heart of assumptions that had driven Allied intelligence estimates throughout the war. Technical Sergeant Romano had spent 6 weeks documenting every maintenance nightmare, hidden within the He-177's coupled nacelles. His analysis revealed failure rates that defied belief among engineers accustomed to American and British aircraft reliability standards. The DB606 engines experienced mechanical problems at rates 60% higher than conventional installations, with heat buildup in the coupled nacelles reaching 200 degrees Fahrenheit, hot enough to boil water, hot enough to ignite fuel vapors, hot enough to crack cylinder heads under normal operating conditions. The dive bombing requirement that had justified the entire program proved to be an engineering fiction that no amount of German technical sophistication could transform into operational reality. Test reports from captured Luftwaffe archives revealed that German pilots considered the He-177 unflyable in dives steeper than 15 degrees. The coupled engines created gyroscopic effects that made recovery from steep dives impossible, turning the theoretical precision dive bomber into an aircraft that could not perform its primary mission without killing its crew. Romano's maintenance analysis provided the most damning evidence of the program's fundamental flaws. You need to remove 47 access panels just to change spark plugs on cylinders 9 through 12, he wrote in his technical summary. On a B-24, it's 4 panels. These aircraft spent more time in hangars than in the air because basic maintenance required major surgery. American engineers at Wright Field studied Romano's documentation with the fascination of professionals examining a textbook example of how sophisticated engineering could produce catastrophic results. The coupled engines represented interesting theory applied without regard to practical requirements. Heat management systems that looked elegant on paper proved inadequate under operational conditions. Access requirements that seemed reasonable in design phase became impossible under field conditions. Squadron leader Eric Brown's flight evaluation from the Royal Aircraft Establishment at Farnborough provided the final piece of Watson's comprehensive analysis. Brown, who had flown more aircraft types than any pilot in history, delivered a verdict that captured the He-177's fundamental contradiction. Potentially excellent airframe, ruined by appalling power plant installation. The coupled engines created more problems than they solved. Brown's test flights revealed flight characteristics that explained why German bomber crews had struggled with aircraft that should have represented the pinnacle of Luftwaffe capability. Single-engine failures in conventional bombers created manageable emergencies. Single-engine failures in the He-177 required shutting down entire coupled power systems, instantly transforming four-engine performance into twin-engine limitations that occurred without warning during critical flight phases. The British test pilots
report documented handling qualities that made the aircraft dangerous in normal operations and lethal in combat conditions. Control response becomes unpredictable when operating on reduced power. Brown wrote, "The aircraft exhibits dangerous stall characteristics when bomb bay doors are open. Recovery from unusual attitudes requires power settings that stress the coupled engines beyond safe operating limits." Watson synthesized months of technical analysis into conclusions that would influence Allied aircraft development for decades. The German innovation that had looked revolutionary from intelligence photographs proved to be a cautionary tale about the dangers of prioritizing theoretical performance over practical engineering. Brilliant minds, forced to solve impossible problems by political requirements, had created solutions that guaranteed failure. German maintenance records captured from Luftwaffe archives revealed operational statistics that told the complete story of the He-177's combat ineffectiveness. Average aircraft availability, 32%. Mean time between engine fires, 100 flight hours. Average time to complete major engine maintenance, 47 hours for coupled systems versus 12 hours for conventional installations. The numbers painted a devastating picture of resources wasted on aircraft that could not maintain combat readiness under operational conditions. While American B-24s and British Lancasters flew daily missions with availability rates exceeding 80%, German bomber squadrons struggled to maintain single-digit operational aircraft numbers despite being equipped with technically superior machinery. Watson's analysis identified the fundamental principles that separated successful innovation from expensive failure. Complexity must serve operational purpose, not theoretical elegance. The coupled engines looked streamlined, but created exponential maintenance problems that negated their aerodynamic advantages. Accessibility mattered more than design theory. The most powerful engine became worthless if mechanics could not service it under field conditions. Heat management represented a non-negotiable requirement that German engineers had attempted to solve through inadequate cooling systems rather than addressing the fundamental problem of cramming two engines into space designed for one. Requirements should drive design decisions, not the reverse. The dive bombing capability that justified the coupled engine installation was itself flawed, but the aircraft design had been distorted to accommodate it. American aircraft manufacturers studied Watson's report with particular attention to its implications for future development programs. The He-177's failure validated Allied engineering philosophy that prioritized reliability over innovation, maintainability over performance, and proven solutions over revolutionary gambles. 4 separate engines meant 4 separate problems that could be solved individually rather than one catastrophic problem that required systematic replacement. British aircraft designers reached similar conclusions about the relationship between theoretical innovation and practical engineering. The Lancaster and Halifax bombers succeeded because they incorporated conventional solutions applied with exceptional competence rather than revolutionary solutions applied inadequately. Individual engine nacelles provided individual access for individual repairs, allowing maintenance crews to keep aircraft operational despite component failures. The captured German documentation revealed that Luftwaffe technical personnel had recognized the coupled engine problems within months of operational deployment, but lacked the institutional authority to demand design changes that would have required acknowledging fundamental flaws in programs approved by the highest levels of Reich leadership. Watson's final assessment became doctrine that would influence military aircraft development through the jet age. The enemy's most advanced bomber was defeated not by our fighters, but by the fundamental laws of engineering physics. Innovation without successful implementation is just expensive failure. By December 1945, the complete picture emerged from German archives, Allied intelligence reports, and interviews with surviving Luftwaffe personnel who finally spoke freely about the technical disasters they had been forbidden to discuss during the war. The He-177 program had consumed 1,094 aircraft, 2,188 coupled engines, and countless man-hours in pursuit of an aerodynamic advantage that proved meaningless in operational reality. At no point during the war had Germany managed to maintain more than 200 combat-ready He-177s simultaneously, despite production numbers that should have equipped entire bomber fleets. German Oberst Johannes Steinhoff, interviewed by Allied technical intelligence officers in a prisoner of war camp outside Munich, delivered the final verdict on the program with the bitter clarity of a professional airman who had watched resources squandered on engineering fantasies. We created a maintenance nightmare in pursuit of an aerodynamic advantage that proved irrelevant, he said, his words carrying the weight of combat experience that contradicted every assumption made in Berlin conference rooms. The He-177's engine spent more time being repaired than running. We would have been better served by conventional four-engine bombers that our mechanics could actually keep flying. The strategic bomber that was supposed to devastate British cities had managed fewer than 50 effective combat missions during its entire service life. Most He-177 sorties ended in mechanical failures, emergency landings, or mission aborts caused by engine problems that occurred, and with predictable regularity. German bomber crews, trained on reliable aircraft like the Heinkel, He-111, and Junkers 88, found themselves flying machines that were more dangerous to their operators than to enemy targets. Watson's technical team had identified the fundamental principles that separated engineering innovation from engineering catastrophe, lessons that would reshape military aircraft development for decades. Complexity must serve operational purpose rather than theoretical elegance. The coupled engines appeared streamlined, but created exponential maintenance problems that negated any aerodynamic advantages. Access requirements mattered more than design theory because the most powerful engine became worthless if mechanics could not service it under combat conditions. Heat management represented a non-negotiable physical law that could not be overcome through engineering wishful thinking. Two engines crammed into space designed for one would always generate more heat than any cooling system designed for that space could dissipate. The thermal problems that destroyed DB606 engines were not design flaws that could be corrected through improved engineering. They were inevitable consequences of fundamental physical constraints. Requirements should drive design decisions rather than the reverse,
But the He-177 program had been distorted by a dive bombing requirement that was itself technically impossible. Aircraft designed to carry strategic bomb loads could not be transformed into precision dive bombers through aerodynamic modifications. The coupled engines that enabled the streamlined profile necessary for high-speed dives also created the mechanical problems that made sustained operations impossible. Allied bomber designs, the B-29 Superfortress, the Avro Lancaster, the Handley Page Halifax, succeeded because they prioritized practical engineering over theoretical innovation. 4 separate engines meant 4 separate problems that could be solved individually rather than one catastrophic system failure that required complete replacement. Individual nacelles provided individual access points for individual repairs, allowing maintenance crews to keep aircraft operational despite component failures. The vindication of Allied engineering philosophy extended beyond mere technical validation to strategic implications that had shaped the war's outcome. American and British bombers achieved operational readiness rates exceeding 80% through conventional solutions applied with exceptional competence. German bombers equipped with revolutionary technology struggled to maintain 30% availability because innovation without reliable implementation was just expensive failure. Modern jet engine development incorporated the He-177's lessons with rigid discipline that prevented repetition of German mistakes. No major aircraft manufacturer attempted coupled power plant
configurations after 1945 because the physical laws that governed heat generation, maintenance access, and mechanical reliability remained unchanged regardless of technological advancement. The principle became embedded in every engineering manual: accessibility first, performance second, elegance never. Technical Sergeant Romano's maintenance philosophy, developed through direct experience with the coupled engine nightmare, influenced American aircraft design standards through the Korean War and beyond. If a mechanic can't reach it with standard tools, it shouldn't be there, became unofficial doctrine that prevented designers from creating maintenance problems in pursuit of theoretical advantages. The practical wisdom gained from German failures proved more valuable than German innovations. Squadron leader Brown's flight test conclusions established evaluation criteria that emphasized operational utility over impressive specifications. Aircraft performance meant nothing if the aircraft could not be maintained in service or operated safely under combat conditions. The He-1. 77's theoretical capabilities became irrelevant when weighed against its practical limitations, establishing precedent for rejecting sophisticated solutions that created more problems than they solved. Watson's final report became required reading at engineering schools and military academies, not as an example of German technical failure, but as a demonstration of how intelligent people could make catastrophic decisions when institutional pressure overrode engineering judgment. The coupled engine concept represented brilliant theoretical work applied to solve the wrong problem, creating solutions that guaranteed failure regardless of implementation quality. The legacy extended beyond aviation into broader principles of technological development that emphasized reliability over innovation, maintainability over performance, and proven methods over revolutionary approaches. The He-1. 77 stood as permanent testimony to the dangers of pursuing engineering elegance at the expense of operational practicality, a cautionary tale written in twisted metal and burned aircraft that no amount of German technical sophistication could overcome. Colonel Watson's concluding words in his technical assessment became doctrine that guided military procurement decisions through the jet age. The enemy's most advanced bomber was defeated not by our fighters, but by the fundamental laws of engineering physics. Innovation without successful implementation is just expensive failure, and the most sophisticated solution that cannot be maintained under operational conditions is no solution at all.